This presentation is on examining base 10. First off, you should have viewed the Introduction to Base 10 video and answered some questions, and those appear in the text on page 133. Some of the tasks in this lab you can complete on your own. Others are usually done as in class as a group. In the middle of page 133, you can see the calendar math description, and rather than modeling this for you, I'm going to let a teacher show you her version of the calendar math.
These are our special cups. We're going to start with the ones cup always. Now the ones cup has to be all the way on this side, on the right. The ones cup is where we add one straw at a time. Every time we add one straw, we have to put it in the ones cup. But the ones cup can only hold 9 straws. After 9 straws, when you put one more in, they all pop out because it becomes a group of 10. We bundle it together and it will move to the tens cup. The ones cup only holds 9 straws. After that, it becomes a group of 10. And we're going to record that to see what that looks like for our number. So let's just practice by adding one straw at a time together. Are you ready? All right, count with me. 1, because we have 1 straw. If I add another one, we have 2. If I add one more, we have 9. Now pause and think. What do we know about the ones cup? It only holds 9. So once I go to put this next straw in, something pretty amazing will happen. We cannot put 10 straws in the ones cup. We can only put 9. Once I try to put this in, they'll all jump out because they become a group of 10. Are you ready? This makes me nervous every time. I'm so afraid I'm going to drop them because I try to put one more in. After I have 9, when I go to 10, I can't stay in there. Are you ready? I get so nervous. Like excited nervous. Oh my goodness, that was a close one. Okay, so now I have 10 straws. This is not 10 individual straws anymore. This is one group of 10. I make them into a unit. I rubber band them together because this group of 10 is special. It moves over to the tens cup. And we're going to record what we have now. I have how many groups of 10? How many tens do I have? 1 group of 10. And how many ones do I have? 0. 1 group of 10 and 0 little ones. Our number here is 10. The number 10 with 2 digits tells us a special code. It tells us we have 1 group of 10 and 0 more ones. The numbers stand for something. They tell us something. So all the numbers in the tens family have 1 group of 10. They start with that 1, but they have different numbers of ones. So let's add some more straws and see what happens. If I have 1 group of 10, whoop, and I add 1 more straw, now I have 1 group of 10 and 1 little one. My number is 11. Do you see that? 1, 1 tells me 1 group of 10 and 1 more 1. 19. Now this is where it gets fun. Are you ready? Stop and think. I have 9 straws in the ones cup. That's as many as it can hold. So when I go to put 1 more straw in the nines cup, what will happen? That's right. They can't stay there. They will become a unit. They will become a group of 10. They will become a group of 10. And where does a group of 10 need to go? In the tens cup. So let's watch and see what happens, and then we'll make our numbers match. You ready? Okay. This is the best part. Oh my goodness. Make sure you catch them if you're doing this at home. Whew. Here's my group of 10. Okay. 1, 2, 3. Oh, this rubber band is old. Let's try this one. I'll be gentle. Okay, so I have a group of 10. It goes in the tens cup. But let's change our number to match what we have. Right here I have how many tens? I have 2 groups of 10, don't I? 2 groups of 10 in the tens cup. How many ones do I have all by themselves? 0. If I have 2 groups of 10 and 0 little ones, what is my number? 20. So when you enter the 20s family, that means every number is 2 groups of 10 and some ones. 2 groups of 10 and some more.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100.
So here you can see various versions of the calendar math. And then on the 100th day, you'll have students come to class, and sometimes they'll have a parade, or you'll have students bring in 100 items, whether that's wearing a shirt with 100 items like you see here. Often you'll see students bring in 100 items that are very different in size, and it's good to sort of experience 100 in various ways, and certainly the students have experienced 100 as far as counting up the days. So there's a big deal around 100 in lots of different ways, particularly in the way that is the development of the base 10 number system. So an important tool in teaching and working with base 10 is the base 10 blocks. And there are lots of different variations of the base 10 blocks, some digital or physical. But in this class, we are looking at virtual base 10 blocks. And one of my favorites is on the mathagon.org site. And so there's a link here for the PolyPad, which is kind of a sandbox where you can play around with lots of different virtual manipulatives, including what they call the number tiles. So using a place value map, which I had to create in PolyPad, it was not one of the standard tools to use, but it's pretty easy to create. And some division between the ones, the tens, and the hundreds, and maybe even the thousands. So we're going to use this place value map and base 10 blocks to model some different numbers. And we'll model 8 and 25 and 101. So first off, let's look at how we could model the number 8. There aren't very many ways. 8 is 8 ones, and that's about all we can do to model using the base 10 blocks. So we put 8 of the single unit squares into the ones place. Next, we'll represent 25. 25 can be represented as 2 tens and 5 ones. And so the tens, the base 10 blocks are made up so that you take 10 of the ones, glue those together in a straight line, and you have 1 10. So 10 ones make up 1 10. And also you can go in reverse and you can take a 10 and break that up into 10 ones. And lastly, here's one representation of 101. The most standard way of looking at 101 is 100 and 1 1. Although we'll see that we can represent 101 or other larger numbers in various ways. So let's deal with this question. How many tens are there in the number 368? Consider that the most common answer might be 6. There are 6 tens because 300, 6 tens, and 8 ones. So let's model 368 to see if we can maybe answer that question in a different way. So here's the most standard way of representing 368 with 3 hundreds or 3 flats, 6 tens or 6 rods, and 8 ones or 8 units. So let's look at another representation. What if I take one of the hundreds and I break it up into 10 tens and move all those tens into the tens place? So now I have 2 hundreds, 16 tens, and 8 ones. I still have 368 total. The value there is still 368, but the representation looks quite different. What if I took one of those tens and broke that up into 10 ones and moved all those ones over into the ones place? So now 368 is represented as 2 hundreds, 15 tens, and 18 ones. We're going to revisit this representation because there might be a reason why we would want to strategically represent 368 that way. This next representation takes another one of the hundreds, moves it over to the tens after breaking it up into 10 tens. So now we have 100, 25 tens, and 18 ones, still representing in total 368. And finally, if we take 2 hundreds, 12 tens, and 48 ones, that's still representing 368. I'm not sure why we would want to represent 368 in that particular way, but we could. We could represent 368 as 2 hundreds, 12 tens, 48 ones. Now, if we address the question of why might it be helpful to have a different representation of 368 other than the standard 3 hundreds, 6 tens, and 8 ones, consider this. What if we're representing 368 with denominations of hundreds, tens, and $1 bills? So suppose you had 368 as 3 hundreds, 6 tens, and 8 ones, but you owed your friend $79. You can't give your friend 7 tens because you only have 6 tens, and you can't give your friend 9 ones because you only have 8 ones. So you need a different representation of $368 that has enough of each place to take away what you owe your friend. If you represent 368 as 2 hundreds, 15 tens, and 18 ones, which is 368, then you can take away 7 tens and 9 ones and give that to your friend. So next, let's talk about a couple of games that you can play with the base 10 blocks. So one of those is called Race to a Flat. And remember before we said 1/100 can also be called a flat. Another game is called Clear the Mat, which has to do with subtraction, where you start with one flat and then you roll the dice and take away however many is on the dice until you get to 0. So in this video, what we're going to do is show a version of Race to a Flat from one player's perspective. The game is called Race to a Flat, and we play this with base 10 blocks and the place value mat. And it's a game where you have 2 players. We'll need a pair of dice, and each player takes turns rolling the dice, and whatever number comes up on the dice, the player represents that number or adds that number to his place value mat. So you accumulate however many along the way, and the first person to make it to 100 wins the game. So this is a good game for practicing counting and adding. So we're going to go through a simulation of this game with just one player, so you can imagine another player is playing in between dice rolls. So first we roll the dice and we get a 2. So we're going to go over and grab 2 and pull those over, put them in the ones place, and now the other player rolls, but now we'll roll again just as though we have one player. So now we have 3 and 5 is 8, so we want to go over and grab 8 and add that to our ones. And notice that we can group those 10 together into one 10. So we'll merge those, we'll regroup those as one 10 and roll the dice again. We roll a 6, so we go over to our bank of ones, grab 6 ones and put them in the ones place. Next we have 7. So here notice that if we already have 6 and we're going to add 7, we can do that in a couple of different ways. The first way we're going to do this is fairly inefficient, what we would expect for kids to do. So that's add 7. So there's 7, and then now we're going to group 10 of those together to make a 10. And we'll take that 10 and move it over to the tens place. So now we have 2 10s and 3 1s. So we roll the dice again. At this point we have 11, which is 1 10 and 1 1, so the job is not too hard here. Rather than moving over 11 ones and then grouping the 10 ones together. So we'll roll the dice again. This time we get a 7, which now we're going to do this a little more efficiently. We need to add 7 to our ones. We already have 4 ones there. So know that adding a 7 is the same as adding a 10 and taking away 3 ones. So we're going to go ahead and grab 3 of those ones to group with the 7, and then just consider that as 1 10. Alright, so now roll the dice again. Now we have 9. Here we're going to be efficient and grab a 10 and take away a 1, because adding a 9 is the same as adding a 10 and taking away a 1. We need to add 3. Add 6. Here we're going to add 8, but adding 8 is the same as adding a 10 and taking away 2. And we would expect the child to become efficient at this game while playing it, rather than starting off with that level of efficiency. We rolled a 4, so now adding a 4 is like adding a 10 and taking away 6, and we do have enough in our ones place to do that. We rolled a 7. We'll just have to add 7. We rolled a 10. That's an easy thing to add. So adding 7 is the same as adding a 10, taking away 3. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 tens. So right now I'm sitting at 95. So one more roll should do it. I've rolled a 6, which is enough. So adding a 6 is the same as adding a 10 and taking away 4. So now I have 10 tens. I'm going to group those together. And that becomes a flat, and I've made it to the end of the game, the objective. So with the base 10 blocks and a place value mat, let's model each of the numbers in the following word problem. Suppose you start with a job delivering the Sunday paper to homes in your town. You have 21 customers to begin with. After word got around, 15 new customers want the paper delivered. How many total paper customers do you have now? So notice that these two numbers should first be modeled separately, one above the other on the mat. So since this is an addition operation, it makes sense to drag the blocks together to the bottom of the mat and then determine the new total. So let's look at what this looks like with the base 10 blocks. First we're going to model 21, and next we model 15. And you can see those modeled separately. And then we push those together, push all the 10s together, push all the 1s together, and then look at how many we have. So we have 3 10s and 6 1s, so we have 36 in total. Let's continue the story. So now you have 36 customers, but because you're doing such a good job, 27 new customers want the paper delivered. So now how many total customers do you have? So again, we're going to model each of the numbers separately, one above the other on the mat, just like before. Again, it makes sense to drag the blocks together to the bottom of the mat to determine the new total. So notice in this case that we're going to need to trade some blocks. We're going to need to rename some of the blocks because the rule always is, just like it was with the calendar math, you can only end up with 9 or less of each of the things, whether it's 1s, 10s, or 100s, in each of the spots. So here we have 36 modeled, 3 10s, 6 1s, and we have the additional customers, the 27, 2 10s, and 7 1s. And we're going to push those together, and we end up with 5 10s, and if we count the 1s, we have 13 1s. So what we're going to need to do is group 10 of those 1s together into 1 10. And move that over into the tens place. So now when we recount how many we have 6 10s and 3 1s. So continuing the story, now we have 63 customers. But because you got a little sloppy, you hit a few cats with the paper, threw some papers in the bushes, now 21 customers have canceled their delivery. So how many total paper customers do you have now? So in this case, each of the numbers should not be modeled separately. You only have 63, and you must remove 21 from the 63. So you may ask, where's the 21 modeled with the base 10 blocks? Well, the 21 is already sitting in the 63. So all we need to do is model the 63 and then subtract away the 21 that represent the customers that canceled their delivery. So here we've represented 63. And notice with the magic of virtual base 10 blocks, I can recolor 21 of those so you can see the 21 there that I'm getting ready to take away. And then when I take those away, we're left with 42. So continuing the story, now we have 42 customers. But because you got a little more sloppy, you hit a customer with the paper, threw some papers at the wrong houses, 18 customers have canceled their delivery. So now how many paper customers do you have? So again, in this case, each of the numbers should not be modeled separately. You only have 42 and you need to remove 18 from the 42. Since this is a subtraction operation and we're treating it like a takeaway context, it makes sense to remove 1 10 and 8 1s from the 4 10 and 2 1s that are modeled on the mat. Here we have 42 modeled, 4 10s and 2 1s. It's a little harder now to see the 18 within the 4 10s and 8 1s. So what I'm going to do is take one of those 10s and break it up to be 10 1s. So now 42 is modeled as 3 10s and 12 1s. And now within the 3 10s and 12 1s, I can more easily see one of those 10s to be removed and 8 of the 1s to be removed. Because remember, we have to subtract 18. And once I do, I'm left with 24. Next, let's look at multiplication. So our first example is going to be 24 times 3. Here's one way I could model 24 times 3 as 24 groups of 3. You can see here I've got the blocks just in the groups of 3, 24 groups of 3. and it's a little cumbersome, but the blocks are set up in such a way that it may be more useful to model 3 groups of 24 rather than 24 groups of 3. So here we've got our repeated addition model. 3 times 24 means 3 24s, 24 plus 24 plus 24. And a 24 is 2 rods and 4 units, so I just need 3 groups of 24. If I put all the 10s together and put all the 1s together, you can see the 10s on the left and the 1s on the right. You can see now I have 6 rods and 12 units. Remember, I can't leave the 12 units as they are, so I'm going to have to exchange 10 units for 1 rod, and now I have 7 rods, or 7 10s, and 2 1s. An alternative to the repeated addition model is the rectangular array model. So again, looking at 3 times 24, 3 times 24 means 3 24s. So if I arrange the base 10 blocks in a rectangular array, I can see 2 rods and 4 units 3 times. So each row has got 24 and there are 3 rows. So if I count the number of blocks being used, again there are 6 rods and 12 units, and I'll exchange 10 units for 1 rod, so I'll have 7 rods and 2 units. Let's look at a couple of problems where we're going to model the dimensions of the array on the outside, and this is representing more of an area model, but it'll still be an array model because the array will still be made up of individual unit squares. So for the problem 13 times 12, we can use 1 rod or 1 10 and 3 units to outline a rectangle whose width is 13, and we can use 1 rod and 2 units to complete the outline of the rectangle whose length is 12. So if we fill in the rectangle using as few base 10 blocks as possible, I'll have the product 13 times 12 represented in the middle. So now if we count the number of blocks being used, there's 1 flat or 100, 5 rods, 5 10s, and 6 1s. So the product is 100 plus 50 plus 6, or 156. So 13 times 12 is 156. So a second example would be 13 times 22. So again, we're going to create a rectangular array where one of the dimensions is 13 and the other dimension is 22. We'll fill in the rectangle using as few base 10 blocks as possible. So if we count the number of blocks being used, we have 2 hundreds, 8 10s, and 6 1s. So the product is 200 plus 80 plus 6, or 286.